Hello, everyone. In this video, we are going to study distances in space. Distances in space. First, let us establish the distance between a plane and a point. This will rely on finding the orthogonal projection of the position vector of the point onto the normal vector of the plane, which leads to the shortest distance between that point and the plane. Consider a plane in space and a point P on the plane, and the normal vector n of the plane that passes through this point. Suppose Q is a point not in the plane. Let U be the vector from point P to point Q. This vector is the vector projection of U onto n. Now, the distance between the plane and the point not in the plane is the norm or the length of the vector projection of U onto n, which is also the absolute value of the scalar component of U onto n. Recall that the scalar component of U onto n is the dot product of the vectors divided by the norm of n. We get the absolute value in case that the dot product is negative. Note that the dot product is negative when the angle between two vectors is greater than 90 but less than 180. That would mean that n and u are on opposite sides of the plane. Given the general form of the equation of a plane, the distance of the point not in the plane to the plane is given by this formula. But how is this dot product the same as these terms inside the absolute value? Substitute the point in the plane into the equation of the plane, because this point is on the plane and therefore must satisfy its equation. So the constant term of the equation of the plane is given by this equation. Note that a, b, and c are all known quantities from the normal vector. Vector u is the vector from the point in the plane to the point not in the plane. Next, compute the dot product of vector u and the normal vector of the plane. Expand. And make this substitution into the equation. Thus, the dot product of the normal vector and vector u is equal to the sum of these terms. Example 1. Find the distance between the plane 4x minus y plus z plus 6 equals 0 and the point 0, 0, 0. Solution 1. We will first use the following formula of distance. A point not in the plane is a given. A quick check to know if a point is in the plane is to substitute its coordinates into the equation of the plane. If the result is not an identity, then the point is not in the plane. And because the point is not in the plane, the distance between the plane and the point is greater than 0. Using the given equation of the plane, we can deduce the normal vector. Substitute the coordinates of the point and the components of the normal vector into the distance formula. Thus, the distance between the plane and the point is square root of 2. Solution 2. We will now use the following formula of distance. Let's find a point in the plane. Substitute any convenient values of x and y into the equation, and then compute the resulting value of z. So those values of x, y, and the resulting value of z make up the point in the plane. A point not in the plane is already given. The position vector of the point not in the plane with respect to the point in the plane is the vector from P to Q. Like in the previous solution, the normal vector can be extracted from the equation of the plane. Substitute the components of the normal and position vectors into the distance formula. Thus, the distance between the plane and the point is square root of 2. Example 2. Find the distance between the plane 4x minus y plus z plus 6 equals 0 and the point 1, 3, negative 7. Solution 1. We will first use the following formula of distance. A point not in the plane is a given. A quick check to know if a point is in the plane is to substitute its coordinates into the equation of the plane. If the result is not an identity, then the point is not in the plane. Because the result is an identity, the given point is in the plane. Hence, the distance between the plane and the point is 0. However, let us proceed by using the distance formula. Using the given equation of the plane, we can deduce the normal vector. Substitute the coordinates of the point and the components of the normal vector into the distance formula. Therefore, the distance between the plane and the point is 0. Solution 2. We will now use the following formula of distance. Let's find a point in the plane. Substitute any convenient values of x and y into the equation, and then compute the resulting value of z. So those values of x, y, and the resulting value of z make up the point in the plane. A point we need to test is actually in the plane, so the distance is 0. But let us proceed with using the distance formula. The position vector of the point not in the plane with respect to the point in the plane is the vector from P to Q. Like in the previous solution, the normal vector can be extracted from the equation of the plane. Substitute the components of the normal and position vectors into the distance formula. Therefore, the distance between the plane and the point is 0. Notice that the dot product is 0. This means that the normal vector of the plane and the position vector are orthogonal. Moreover, the position vector PQ lies in the plane. Distance between two parallel planes. Recall that parallel planes have normal vectors that are scalar multiple of each other. Suppose P1 is a point in plane 1. Let N2 be the normal vector of plane 2. If we draw a right triangle involving vector N2 and vector U, we can compute the distance between the parallel planes as the distance between a plane and a point in the other plane. And it is the norm of the vector projection of U onto N2. Meanwhile, if we use the equation of plane 2, the distance is given by this formula. The computed distance will be the same anywhere because the length of the projection is going to be the same, no matter which points in the planes are used. Note that we can use this approach if we have a point in plane 2 and the normal vector of plane 1 instead. This formula provides the distance between two parallel planes. But what kind of distance does the formula give if used for planes that are not parallel? What if the planes are not parallel? Let us draw the same setup, except that the planes are not parallel. Consider one of the planes, and a point in the other plane. Form a right triangle involving the normal vector of the plane, the position vector of the point in the other plane, and the projection of the position vector onto the normal vector. The computed distance would be the distance between a plane and just a point, as if the other plane was not there. So the distance formula would be the same as the distance formula between a plane and a point not in the plane. But the computed distance changes depending on the location of the point in the other plane. Example 1. Find the distance between the planes 2x plus 3y minus c plus 1 equals 0 and negative 6x minus 9y plus 3z minus 8 equals 0. Solution. We will use the following distance formula. The normal vector of a plane can be extracted from the equation of the plane. We notice that normal vector 1 is negative 3 times normal vector 2. The normal vectors are scalar multiples of each other, so the normal vectors are parallel. Hence, the planes are parallel as well. Find a point in plane 1. Substitute convenient values of x and y into the equation of plane 1, and then compute the resulting value of z. So those values of x, y, and the resulting value of z make up the point in the plane. Use the normal vector of the second plane. Substitute the coordinates of the point in one plane and the components of the normal vector of the other plane into the distance formula. Therefore, the distance between the two planes is 5 all over 3 times the square root of 14. Example 2. Find the distance between the planes negative x plus 2y minus 3z minus 10 equals 0 and negative x plus 2y minus 3z plus 10 equals 0. Solution. We can use the following distance formula. The normal vector of the two planes can be extracted from the equation of each plane. They are still scalar multiples, but the scalar is just 1. It means that they are parallel vectors. So the planes are parallel as well. Both planes have the same normal vectors, so let us just give them the same name. Instead of finding a point in one of the planes and using the formula above, let us try a different approach to calculate the distance between the two parallel planes. So there are two planes with equal normal vectors, but the constant terms of their equations are different. Which means the two planes are parallel but not exactly the same planes. For a point in the first plane, that point must satisfy the equation of the first plane. So the sum of these terms is equal to the negative of the constant term of the equation. Let us rewrite the distance formula for two parallel planes. This formula is originally for the distance between a plane and a point not in the plane. For the distance between the point and the second plane, This constant term is the constant term for the second plane. And the sum of these terms are equal to the negative of the constant term for the first plane. So this is now the distance formula for two parallel planes with equal normal vectors. Substitute the required quantities. Therefore, the distance between the two parallel planes is 20 over the square root of 14. So let us summarize computing the distance between two parallel planes. There is a general formula for two parallel planes whose normal vectors are scalar multiples. It needs a point in one plane, and the normal vector, and the constant term of the equation of the other plane. But if the normal vectors are equal, the distance can also be computed using another formula. It needs the constant term of the equation of each plane, and the normal vector, which is the same for both planes. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.